MCQ and 20 marks short answer type, right?
Pardon?
30 marks MCQ and 20 marks short answer types.
Okay. Any other thing you know about any other modification?
No, sir.
What is the exam date?
Exam date CN is on
Second.
2nd May.
2nd May. Okay. Okay, so I have given you an assignment in module 5 since the time is less. Okay, so you have to write it and submit it in the handwritten form. So we will have doubt classes in the next week. I have already posted it, and that will be held in the physical mode. Okay, since there is only 1 week left, so everybody should be on campus, and for the exam. So I expect that you people will come for the class, and there are another 10 marks. Okay, that will be the teacher's assessment. Okay, so since I know, do you know about the teacher's assessment part?
Yes, sir.
So how will it be done?
So HOD sir said based on attendance, day-to-day performance.
So if I go by attendance, hardly you only 7-8 students will get the some marks. The 7-8 also I set a big number. If I have to give, I will give only to 3 students. Okay. So please convey this message to everyone. So 10 marks and then later nobody should complain that I got less marks. So it will not be purely based on the attendance, right? That will be an injustice because we didn't announce the attendance marks earlier. But as per my observation, who all are responding, who all are not attending the classes, right? How you are joining, how late you are joining the classes. So that will all take into account. कौन कब join कर रहा है, कौन कब कितना actively participation है. Everything will come, and whoever is turning up in the doubt classes, that will also be included. Okay. So as regarding the tutorial sheet, I will give tutorial sheet by tomorrow or day after tomorrow morning. I have it. I have to search it. And if you need the old question papers, I can give it right away. Okay. But I have to scan them. Okay. Anything else you want to say?
Sir, module 5 study materials, PPTs.
That I will upload. You can use William Stalling book. It is William Stalling 7th edition or 8th edition, whatever it is. You can use that. Otherwise, whatever I have, I will upload it. Right?
Thank you, sir.
Sir, and in the quiz, I had one doubt that when a SYN flag is sent and the system is idle, it is received by an acknowledgement, right?
No, it should be reset, RST.
But acknowledgement is also sent together.
No, actually, the system is idle. That if you go by a transition diagram, state diagram, you will see that when a system is in idle condition, that means it is passively open. It is not actively open. So any connection request coming as a SYN will be rejected with an RST.
I had read the three-way communication in that it was like...
That is a different thing. That three-way is like that will prevent from obsolete SYN segments. Okay, if a SYN arrives after the close of a connection or in the same connection, means the obsolete SYN segment or an like a delayed SYN or delayed segments appearance will not create an issue if we are using a three-way handshaking, right? But actually, it is the question was, if I remember it correctly, that when a transport entity is in the passive state, right? It is not able, it is not ready to listen to anything. Then in that case, it will simply reject the request by RST command.
Okay.
Okay, we can discuss these things in the class. Even the questions can be discussed, right? So 3 doubt classes I have kept, and Possibly what could I do in the fourth module, I will see, right? So before going to this part, right, I just want to take you to the ciphers. See, these things are important, though they are not in your syllabus. But without knowing them, you cannot understand DES and AES, right? Because they are the inherent part of that. So in the previous class, we discussed about that the different ciphers. Ciphers means like how you encrypt and decrypt. So we discussed, I think, this, that if a plain text is given, that how the ciphers can be substitutional ciphers, traditional ciphers, right? So traditional ciphers we had substitution ciphers, transposition ciphers. Substitution mein there is a monoalphabetic and there is a polyalphabetic, right? Every time if a character is appearing, it will replace with the same character, right? A will always be replaced with Z whenever it is appearing in the text. So like that, that is monoalphabetic substitution. But in a polyalphabetic substitution, whenever a character A appears, it will be replaced every time with a new character. At the first instant, it is replaced with L. Next instant, it is replaced with Z. Third instance, it may be replaced with D. So it is depending on as and when it is appearing, it will be replaced with a new character, right? So there is a key. So this examples we have already discussed, that what is the plain text and what will be the cipher text, right? And there was an additive cipher that is also oftenly called as Caesar's cipher, right? That Julius Caesar used it. So it is additive cipher. So key is 15. So you will be just adding this position of this character by 15 times, right? And then you're substituting it. So it's a kind of a substitution cipher only. So, so this example also we had seen it in the previous class. And similarly, how the decryption can be done in the other way. If a key is given as 15, so from the current position like W is 22, so 22 minus 15 is 7. So it will be replaced with H, right? So if the word is W, so W 15, we advanced the position of the alphabet by 15 elements, okay, because the key size was 15. So just to go for a in the reverse way for decryption part, so this will be 22 position, it is currently W. So it will be 15 will be minus, because we have to go back to the actual position. So actual position is 15 steps back. So that will be 7. So H, that is H, right? So now coming to the transposition ciphers. The transposition ciphers, like where you perform some sort of a transposition, like this bit, right? Suppose you are going to say about this text, hello my dear. So this is what the plain text, this is given as a plain text block. Then you encrypt this using this way, right? This is an encryption process, like the first will go to the third, second will go to first will go to third, okay, second will go to fourth, like that. So this is what an encryption process, and in the decryption process, the reverse will be followed, right? So once again, we will put back. So transposition means just changing the position of the elements, right? इसको यहाँ ले गए, उसको यहाँ लाए, right? Just changing the positions, and this is called as a transposition cipher. There are different types of cipher in the transposition cipher. So we cannot cover everything, but just like you have to encrypt the message like hello my dear. So how do we do that? First of all, what we do, we divide into 4 characters. Okay, spaces are removed in the message. Okay, and it is divided into a text into blocks of 4 characters. So L, O, M, Y, D, and then the last one is 3 characters. So we append a bogus character Z at the end, so that we can maintain a 4 character uniformity, right? So once we have done that 4 character and putting a bogus character at the end, so then this will, we will change it as per this key, right? As per this key, the first character will go to the third position, right? While encryption, okay, the first will go to third, second will go to first. So you can see here, the first will go to third, second will go to first, and this third will go to fourth, and fourth will go to second, right? The fourth will go to second. So you can see here, the first has gone to third, the second has gone to first, third has gone to fourth, and fourth has gone to second position, right? So we have encrypted it in this way. And when the same thing appears at the receiver end, we perform the reverse of it, right? Reverse means like just the first will go to second position, second will go to fourth. So it will be just a reversible thing, right? So once this reaches here, we just perform the bogus character, we remove the bogus characters, and combining the characters, we get back the original message, right? So there are like XOR cipher, it is widely used because you know the property of an XOR operation that it is reversible. Because if any input is given and an XOR operation is performed, you will get some output. And once again, this output is XORed with, once again it is XORed, you will get the same input, right? Suppose if I am giving a key, okay, this input along with the key, I am XORing it. I will get an output, and then from the output, if I want to get back to the input, it is a reversible process, right? Rotation cipher. So you can rotate it like, you can go to shift left, you can go to shift right. Okay, just what you have studied in microprocessor, you can go to shift left. So the this bit will go to the left position or to the right position. Then accordingly, all other bits will shift, right? Shift left, shift right. So rotation ciphers, right? Then comes the substitution boxes. Okay, you will find there are different types of substitution boxes. We say that there is a diffusion boxes, D box. P box is called as a permutation boxes. Okay. And like B box, it is called as a diffusion box. P box, permutation. And simply S box is called as a substitution box. So substitution boxes are like, there are n input bits, okay, there will be m output bits. So there is basically a function that matches n inputs to m outputs. So if you are getting equal, if n and m are equal, right, if you are getting an n bit input and you will be getting an m bit output, then it is called as a non-invertible. Okay, invertible, because you can revert it back. But there are cases, right, where I will say that the compression boxes, okay, where suppose, yeah, like this, you can see here, this is what a straight box. Okay, straight means you will be putting one at this fifth position, for fourth position, second at one, third at fifth, like that. But there are chances like where you need to expand it or you need to compress it. So here you are giving only 3 input bits, right? And what is the output? Output is 5 bits. These are called expansion boxes. So here this operation is non-invertible. क्योंकि कौन किसी 2 बिट को तो आपको 2 एक्स्ट्रा बिट ऐड करना पड़ा ना, यहाँ पे एक ही this 2, like you see here, this 1 is mapped at 2 position, at position 1 and at position 4, right? 3 is also mapped at 2 position 2 and position 5. So that is how the 3-bit input is being expanded to 5 bits, right? And on the other end, if you see here, it is a compression box. So some of the inputs are to be dropped. Okay, you can see that the input 1 and input 5 are dropped. They are not part of a output bits, right? So two of the inputs are dropped. So that means out of 5 bits, only 3 outputs are generated. So that means some of the input bits are dropped. So in this case, when I am saying about the expansion or compression boxes, there is no possibility that you can revert back. Suppose if you have done something, some operation, the reverse of that is not true, right? So these two operations are non-reversible, but these straight boxes are reversible, right? Whatever you are doing, the reverse can be performed. Okay. So there are permutation boxes, there are expansion boxes. Okay. So before going to this DES, okay, is there any doubt?
No, sir.
No, sir.
So how this substitution boxes works, I would like to tell you that you just see this leftmost bit. Okay, this leftmost bit here, this leftmost bit says about the column. Okay. So here we have the input that this leftmost bit will say about the column, and these two bits, sorry, this will say about the row, and this will say about the column. Okay. So whatever input you are giving, row 0, column 0 0, so you are giving replacing. This is what the output of that 0 0 1 1 1 0 1 0, right? So this is what the substitution boxes. We will see in DES. We will see how the substitution works, right? So these are called S box, P box, D box. You will listen these things: diffusion boxes, permutation boxes, and substitution boxes, right? So with this, I am going to show you about this DES. Okay. So we started with ciphers. So you have seen that there are rotor machines that was used in the past. Okay, some that has history. The classical ones have substitution and transposition ciphers. Modern ciphers, which are called modern block ciphers. Modern ciphers are using this private key encryption and public key. So private key is one where there will be only a single secret key that will be used for encryption and decryption both. Okay. On a public key there will be a private key and there is a public key, right? This is also called as an asymmetric key. So that we will discuss. And in that private key, there is a stream cipher and there is a block cipher, right? So stream cipher and block cipher. You know that the block cipher, we basically divide the data stream into blocks. Okay. So we process the plain text input in fixed size blocks and produces a block of cipher text of equal size for each plain text block. Right? It is symmetric. So symmetric means there are two examples. One is called the DES, Data Encryption Standard, which is basically given by IBM in 1970s. I think I have told you in the history part. Okay. So this is basically DEA or DES, that is data encryption algorithm, and there is a triple DES, okay, which is just given to improve the security of this DES because this DES was compromised. What was single DES that was compromised? So a triple DES is given, but there is a computational load is increased, and so which is more which is substituted with AES with slight modifications, right? That is called as an advanced encryption standard. So we will be discussing this DES and AES. So you know that what are the requirements for security, that you require a strong encryption algorithm. So even the encryption algorithm is known, the intruder should not be unable to decrypt without key. So if you have a combination of many plain text and ciphertext, you should not be the intruder should not be able to decrypt anything. So they should securely obtain secret key. That is what I told you about the symmetric key encryption. There is a problem of key distribution because the same key is to be utilized for the encryption part and at the description part. So how the two users will exchange the secure key over the internet or over the public network. So that is again a big challenge. So once a key is known, all communication using this key is readable. So if in any case, if the key is in the hands of the intruder, all your communications will be compromised. So what are the different types of attacking encryptions? Cryptanalysis, I told you that what kind of algorithm you are using, what kind of output you are generating, what is the key length and everything. If this is what an intruder can perform, it is a part of a passive attack, cryptanalysis, right? So if somebody has got some knowledge about the algorithm and general characteristics of the plain text, it can attempt to deduce plain text or the key. So that is what the cryptanalysis, just going through the ciphertext and getting it. If some knowledge of plain text or key is there, it can be this data can be compromised, right? Another one is a brute force. So like sometimes if you forget to log, if you remember that cycle log that has numbers from 0 to 9, so you put some 3 numbers, right? So it's what sometimes you forget and you do the hit and try. So that is what a brute force attack. Try every possible key until plain text is recovered. And it's not a big deal when we are talking about today's generation resources. So I have one example here. So if you see here that how the brute force attack takes place. So if your key size is 32 bits, so total number of possible combinations are this, right? So that is how much time is required to encryption. 2 to the power 31 microseconds, and that is 5.8 minutes. Or so this is what the time for key search, right? So you can see with increasing key size, you can see here, you can see, right? So with the current resources, right, the capability of the current resources, it is very easy to perform a brute force analysis, right? So the key length should be, there should be a sufficient key length. There are standards. NIST has given some standard. ऐसा भी नहीं है कि we can take a key length of 1000 bits, 1000 bytes, okay, or bits. So that is not feasible also. So we need to have a balance, right? So how the DES and AES works on it, we will be seeing this. So before going to the DES, right, I will tell you about the cipher which is used, which is known as a Feastel cipher, which is just we substitute each round in this DES algorithm. Okay, each round, you can see there are 16 rounds. This is a DES encryption scheme. Here we have an initial permutation because 64-bit, it takes a 64-bit plain text, okay, and a 64-bit key. Out of the 64-bit key, there are 8 parity bits which are dropped. Okay, so remaining are 56 bits. So out of each 56 bit, there is a round key generator which generates every time a 48-bit key in each round. Okay, and this round is nothing but a Feastel cipher. Each round comprises of a Feastel cipher. So there are 16 Feastel ciphers here, 16 rounds of Feastel ciphers. Right, every round has got a different key. Okay, so we are going to see, and then there is a swap that will swap the 32-bit block to this way, and then inverse initial permutation. So there is a final permutation that will just reverse the process of this initial permutation, so that you will get a 64-bit ciphertext, right? So each round is a Feastel cipher. So what is Feastel cipher? I will take you first to the Feastal cipher. These are called product ciphers. Okay, there are two types of product ciphers. One, I'm directly going into the detail of this Feastal cipher. There are two types of Feastal ciphers. One is called Feastal, another is called a non-Feastal. Feastal means which uses which is invertible. Okay, non-Feastal is AES. Okay, on Feastal cipher it is DES, non-Feastal it is AES, because it has got an a Feastal cipher has got a self-invertible block, invertible and non-invertible. So if it has got a non-invertible block, then how it performs that encryption? Once you're performing the encryption, how will you decrypt it, right? If it is using a non-invertible, so it is done with the help of a XOR operation. So you can see this is what the plain text is given. This was the first thought of Feastal cipher, right? That the entire plain text is given over here, right? So it is mixed. What is a mixer? Mixer mein hum log kya kar rahe hain? There is a key is given, key, and this key this key is mixed with the plain text using it is XORed. This key is XORed with the plain text. So this operation is called as a mixer operation. Then you get a cipher text C1. Okay, and you perform the reverse because you are doing an XOR operation. So whatever you are doing, it can be reversible. So C2, whatever you have got, that is a cipher text, you transmitted encrypted one at the decrypted end, you got C2, that is again mixer. The same key is given and it is decrypted using a function. I will tell about this function. You get the plain text back. So you can see here C1 is P1 exclusive or F of K, function of key. Okay, decryption mein, so you get back to P1. P2 is C2 exclusive or F of K. So C1 and C2 are same. If I believe that the whatever I transmitted, the same is received at the other end. C2 can be replaced with C1. C1 exclusive or FK is nothing but I can say C1 is what? P1 exclusive or F of K, right? So that is C1. So this is what C1 exclusive or F of K. So this exclusive or will be cancelled out. So what I will get? P1. So this was the initial thought for that the similar terms will be cancelled out. So existence of inverse and existence of identity. So the two property of exclusive OR are used. So you can see here the mixer has a non-invertible element. The mixer itself is self-invertible, right? So this is called, this was the first thought, right? So the final design came in that we divided this entire plain text into two halves. Suppose if I have a 64-bit input, this is given 32-bit, this is given 32-bit, right? So 32, 32, 64 go. So ये list left half, this left half 30-bit, 32-bit is mixed with the key, right? The right half, it is mixed with the key, right? And the right half is placed directly over here. So this key is mixed with the right half plain text and the left half plain text, and it is put over here L2. So what is transmitted here is again revertible back to this. But this operation has a flow that this R2 is transmitted as it is. What is this R1? The same is here R2. So this can be compromised. So to avoid that, there is a swapper operation is added at the end, the Feastal cipher. So this swapper is added. So this will bring this to this position, right? Swapper. This R1 will be put here and this L1 will come over here, the swapper operation. So this is what a round one. So you can see that this left half 32-bit, okay, you will see that it is given here. I will share this, that you will get exactly R4 equal to R3 equal to R2 equal to R1, right? and then that L4 is equal to L1. You can see here that the same exclusive OR operation we are doing it here, right? So it is reversible. So in each round one, so this is a mixer network followed by a swapper. Okay. So here what we are doing, we are just in the mixer, we are mixing the key and the rightmost plain text bits with this leftmost plain text bit, and we'll be keeping it here, right? And this will be keeping it here. So this is what swap operation followed by the mixer, right? Non-Feastel ciphers uses only invertible component. That is what based on that AES is based on that. So I hope it is clear that this each round has got a one Feastel cipher, right? Is there any doubt? So we saw that in in the DES algorithm, there is an initial permutation and there is a final permutation. So how does it work? You just see that how the initial and final permutation works. You can see here that there are 16 rounds. Before that, in the beginning, there is an initial permutation. So that says that the first bit will go to which position. Okay, second bit will go to which position. So this is all fixed permutation, like shifting first to fourth, fifth to this, and so this is basically a table marked with the first one, that the first bit goes to the 58th position, the second bit goes to the 50th position, third goes to the 42nd position, right? So initial permutation. Okay, so if you see here the 58th position, this is 58, so this is 1 1, right? 50, if you see it will be 58, then 50, 58 is 2, right? So this is what an initial permutation which is done over here. So first goes to the 58, second goes to the other place, like the 50th position. So these two permutations have no cryptography significance in DES. Both permutations are keyless and predetermined. So these are predetermined, right? So they are, why they have been put like that, just to increase the level of complexity only they are put into it, just because of that. Then after the initial permutation, there are 16 rounds. As I told you that each round is a Feastel cipher like this, right? Mixer followed by a swapper. And what is this function basically? What is this function? This function is called as a DES function, right? So what exactly it is doing in the mixer, which is non-invertible, right? This mixer, whatever function you are doing, that is non-invertible, because once the key is given and the rightmost bits are given, and how they are mixed with the leftmost bits. So that we have to see. So how this function works. So that function is called as a DES function. So what is the DES function? Here it is DES function. You can see here the input is 32 bits. In this, the input is 32 bits, right? In this DES function, the input is 32 bits. So this, we put an expansion T box. Why? Because what is the key length? I told you there are 64-bit key. Out of that, there are 8 parity bits which are dropped. Remaining are 56 bits. Out of 56, 48-bit key is generated by a round key generator. So every round, there is a 48-bit key generated. So since the key length is 48 bits, so we use an expansion D box. So that is why I said that this particular operation, this DES function is non-invertible, because 32 bits you are expanding to 48 bits. So some of the bits will be put at multiple positions. So like that, you can see that how this expansion works first, right? So we divided these 32 bits into a group of 4, 4, 4. So this 4th bit, okay, is sent to the 5th bit position, and this 5th bit is put into this position. So like that, These 4 bits are expanded to 6 bits. So 6 8 the 48, right? So how this is expanded? You can see here how it is expanded from 4 bit to 6 bits. So each, so we got a 48 bits expansion D-box output, right? And then since now it matches with the key length, so it is XORed with the key. So we get a 48-bit output, right? So this is what the rightmost 32 bits I am saying. These are the rightmost 32 bits which are XORed with the key. Okay, so we got a 48 bits output. So then it is substituted into the substitution boxes. Okay, these substitution boxes. So this is what the table of expansion D box, that the 32 bit, that this which bit goes where, right? Then substitution boxes. So here you will be given a 6-bit input. Okay, and what do you want an expect output? 4-bit output. So you can see here, this is what a 6 bits, and this looks like the substitution box. How we get a 4-bit output? Okay, so once again we will be going to use a compression technique, right? So to shrink our output to 4 bits, so 2 bits are to be dropped. So how they are to be dropped? So you can see here we have this identify this bit and this bit. The first bit and 6th bit will identify the row. Okay, following the first bit and 6th bit will identify the row, and these 4 bits will be put in the column. So you can see here, like these are the rows, these are the columns. Okay, so they are, each box follows a predetermined rule based on a 4 rows by 16 column table. There are 4 rows with a 16 column table. The combination of bits 1 and 6 of the input defines one of the 4 rows, right? 0 0, row 0 0 1 1 0 1 1. So they define the 4 rows and 16 columns. These bits define the intermediate 4 bits define the 16 columns, right? Just like I told you earlier that so we need 8 tables. We need 8 tables, 8 such tables. Okay, because you have this substitution box 1, 2, 3, 4, 5, 6, 7, 8. 48 bits input, hai na? So we require 8 substitution boxes. So 8 substitution tables are required. So let us see how does it work. You can see here. So each S box has its own table. We need 8 tables. The value of the input row number and column number and the value of the outputs are given as decimal number to save space. So here you see that 0, 1, 2, 3, right? If these bits are 1, 1, if you give some input here, okay, 1, 1, these are 1, 1, so these are 3, so 12. So 0, 0, 1, 3, then 1. So this bits is 0, 0, 0, 1. So that will be replaced with 12. 0, 0, 0, 2, 0, 0, 1, 0. So that will be replaced with 8. Right? So like that, these are substitutions, these are predetermined. Right? So like that, there will be 8 substitution tables. So if this is the, you can see here the input to S box is this. What is the output? So you can see this is 1, 1 is what? Showing the bit 1 and bit 6 is showing the row. So 1, 1 means row 3. What is the number? 0, 0, 0, 1. So this is 1. So it should be 12, right? In decimal. 12. So this is about the DES algorithm. So there are 16 rounds. Okay, for each round is like this. Okay, having a Feastel cipher. Feastel cipher, in that there is a DES function which is non-invertible. So what is the DES function? This DES function is this. right? Which comprises of an expansion D box, substitution boxes, and then straight D box. Straight D box will what? 32-bit output will be passed to a 32-bit output, right? And then there will be a final permutation. Final permutation will be based on this. That जो आपने initial किया था उसका ही reverse process होगा final permutation, so that you get the actual thing, actual plain text. So how the key is generated? So you can see that the parity bits, as I said, there are 64-bit key initially if you see. Okay, so parity bits are dropped first. So what are the parity bits? 8, 16, 24, 32, 64. So those 8 parity bits are dropped first. So what is the remaining is 59. 56 bits are remaining. So 56 is divided into 2 parts, 28, 28. So they are shifted left, right? And it is also mentioned that how much shift it will be there. So for different rounds, like round 1, 2, 9 and 16, there will be 1-bit shift. And for others, there will be 2-bit shift, right? So in round 1, there will be only 1-bit shift. So you get, how do you get a key? Out of 56, this compression D box, you get a 48 bits key, right? And this shift operation will be, because this is round 1, so it will be one time left, and then out of that, this random key is generated. But when you go to other rounds, except 1, 2, 9 and 16, there will be 2 left shift, right? For each side, for each half. This is how we generate the key. So this is about the DES algorithm. So initial permutation, final permutation. This is a round key generator. 64 bit से कैसे 48 bit का key आ रहा है? You have seen, right? Each round is a Feastel cipher. Okay, that has got a non-invertible function that is called as a DES function, that basically comprises of a diffusion boxes. Okay, expansion D box, because 32-bit input आता है, 32-bit को we converted to 48 bits, right? Then 48 bits input output is mixed with 48-bit key, XORed करते हैं, then we got a 48-bit output. So we put that into an 8 substitution boxes. Substitution boxes output comes out to be 32 bits. How do we do it? Because the 6 bits, first and 6 bits says about the row, and the in between 4 bits says about the column. And these substitution boxes are predefined. And then we got a straight D box to give, that gives an output of 32-bit, right? And from the left half, it comes out. So this is like this. So this left half is going with this, right? And this right half is going swapped, right? It is swapped also. So you see this left half is XORed with this function of right half and key. So this is XORed, then this is again XORed, and then we put it here. So the swapper operation was added to overcome the drawback, because the right portion was going just transparent. There was no function added, so anybody can guess this right portion. So a swapper operation was added in the Feastel cipher, right? So in a trip, so any doubt in the DES algorithm? Any doubt? Any doubt?
No, sir.
So then, since DES couldn't, so this is about all details, right? You can see that DES was developed by NIST. So its key size was 56 bits and the blocks are of 64 bits. Right? So this DES, first of all, the key length was so small, okay, that can easily be compromised. Okay, so that is why this has got this DES algorithm was broken. Okay, so in 1998, the Electronic Frontier Foundation announced that it has broken DES. Right? So in 1997, NIST came with a 128-bit key block size, and this block size was also very small. So it uses 128 block size and a key length of minimum 128 bits. Right? So the key length is 128 bits, so 2 to the power 128. And AES works in 3 different key sets: 128, 192, and 224. 256. Right? So just to have it equivalent to that, double and triple DES were also used. So what was double and triple DES? It uses three keys and 3 execution of DEA. So basically 3 algorithms of DES is put together, right? So its key length is becoming 168 bits. So what was there in the triple DES? You just see so there are triple DES means each round is basically a DES algorithm. Encrypt DES, decrypt DES, and then encrypt DES. So each round has got 3 DES. Okay, that is why it is named as triple DES. But still, it was not that powerful to compete with AES. So AES has given change to this 128-bit block size. There are 3 rounds, 10, 12, and 14 rounds, and each round has got a minimum of 128-bit key. Right? So once again, for AES, we should understand some basic part. So DES could fail to stand in front of brute force attack, differential cryptanalysis attack, and linear cryptanalysis attacks. Right? So that is what happened with this DES. So now moving to AES. Okay. AES is so it basically 3 executions of DES algorithm, but it is very slow and block size is too small, right? So advanced encryption standards were proposed. So security strength equal to or better than 3 DES. It significantly improved efficiency. Okay, so this is all I have told, that there are 3 key sizes in 3 different rounds: 10, 12, and 16 rounds. So it inputs a 128-bit block, square matrix of bytes, okay, copied into state array, modified at each stage. So after final stage, state copied to output. You can see here, this is what an AES encryption and decryption process, right? So here, each round output is called one state. Okay. You know that what is data units, that you know about byte, okay, 8-bit byte, okay, V0 to B7, right? And you can write this byte in this form also, V0 to V7, right? Transpose of it. So this byte can be treated as a row matrix or a column matrix, right? So when it is treated as a row matrix, the bits are inserted from left to right. When treated as a column matrix, the bits are inserted into the matrix from top to bottom. Okay. So, and you know what is a word? Word, can you say what is a word? You know bit. Bit is the smallest unit. Byte.
8 bits.
Huh?
8 bits is equal to 1 word.
That basically 32 bits is a one word. 8 bits is a byte. 8 bit is a byte. And 32 bits is a word. And there is a double word of 64 bits. Right? Then long word 128 bits. Right? So word basically is a 32 bits that can be treated as a single entity. So that can be considered as a row matrix of 4 bytes. So a single word जो है W0, so this will be considered as a single row matrix of 4 bytes, right? So we represent this data in the form of words. So there are basically 8 words. 8 hoga? Yeah. So you just see here that there are 4. I will come to the key, how a key generated, right? So you can see here that 128-bit key we are using. So 128-bit key is divided into, I will show you an example. Can you just remember this diagram? Add round key, plain text, add round key. Then this is basically a round that has some invertible operations. As I told you, this is based on non-fiscal cipher. Here we have a invertible operation, substitution bytes. Substitute करोगे वापस से उसको उस position में ला सकते हो. Shift rows, mix columns, add round key, right? So this is one round. I'm just going back to an example. You just see this example. So my key is, that's my kung fu. So this is my key. So there are 16 ASCII characters of 1 byte each. That's my kung fu. So this is written in the ASCII 54, 68, A61, T. So as per the ASCII, we have written this and in hex. Okay. So this is what my key. This is what my key, right? And what is my plain text? Plain text is 2192. So again 16 ASCII characters, 1 byte each. So I have just converted into ASCII equivalent and written in hex, right? TWO, like that. Space 20, space 20, space 20. Then what is the first round key? See, every round we generate a new key. Okay, you can see here we generate a different key. This key is related, this key is generated derived from the previous part, from the previous thing. Okay, so how it is done, you just see that key is in hex this. Okay, so it's a hex number. Hex, you know, it's a representation of 4 this. So what is word 0? Each word is a 32-bit number. So we wrote 4 bytes, 54, 68, 61, 74. This is word 0, word 1, word 2, word 3, and like that we have represented into 4 words. This 4 32-bit words. This key, right? So how we get this key generated for the first round? Okay, how the first round key is generated? So we first this W3, we circular shift byte left shift of W3. एक बार इसको left shift किया. Okay, so left shift means the 67 will be here. Then you can see here the algorithm that add round key. So we have just shifted it once, and then substitution bytes as box. So from the as box, these numbers, okay, are substituted to this B7, 5A, 90, 85. कैसे? You can see here. So this is what a predetermined rule. From a predetermined rule, this is shifted to substituted to B7. I think somewhere it is there. Okay, so this is just a fixation. इसको हमने ये लिखा, इसको हमने ये लिखा, इसको हमने ये लिखा, इसको हमने ये लिखा, right? Then adding round constant. Okay, we will do it in the next class. Its time is over, so we will do it tomorrow. This thing. Okay. Thank you all.
Thank you, sir.
Sir, can you please upload the material which you are teaching?
Okay, sure.
Thank you, sir.